This is Qt 5 Design Pattern Section 4. We're going to talk about memory, and we often overlook this, especially when we're way beyond the advanced part of C++ and we're just in our zone and we're coding. So we're going to dial it back. We're going to talk about the stack, the heap, memory leaks and stale pointers, along with how Qt does memory management, including the parent-child relationships, RAII, and smart pointers. In this video, we're going to talk about something relatively safe, memory, but we're going to talk about the stack specifically. So this section is going to deal with memory management, something that we typically take for granted, but in C++ and especially Qt, we have to worry about. So the QObject class is pretty simple, pretty easy to understand. If you're taking this course, you're probably rolling your eyes and going, why are we even talking about QObject? Well, it's because QObject is the building block of pretty much everything in Qt, and because of that, it has its own little gotchas. Namely, you cannot copy a QObject. I'm going to say that one more time. You cannot copy a QObject. You can clone a QObject and you make a pointer to a QObject, but you cannot copy a QObject. And, well, that's because of this little guy here, the QDisableCopy. This thing will frustrate you to no end, especially when you're just starting off on Qt, or if you're trying to review somebody else's code and they don't understand this. This little guy will basically remove the copy constructor or disables them from any QObject. So if you try to copy it, it's going to throw an error. And there are a bunch of lengthy, reasons why. This guy right here, Alex, he has one of the best descriptions out there. So I'm actually going to put a link right in my description. But it really dives into why, and I can summarize this whole thing for you that Qt's design philosophy is that each QObject is an independent, unique object, and therefore should not be copied, because if you copy that, you're now copying all the signals and slots and all the interconnections that Qt uses under the hood to track what that object is. So if you now take that object and make an exact copy of it, but then delete the copy, how is your application supposed to function? It gets a little confusing. So let's dive in here. Take a look. And I'm just going to copy my notes here. Lots and lots of notes. Notes probably going to be bigger than the actual program. But really, what is the stack? Well, it's a chunk of memory that when your application is created, the operating system says, I bestow upon thee this memory. And you can find that in most operating systems. I think most Linux, Unix, Mac, Windows, you may need something different. Using the ulimit, and you can find through S and A what they actually are. So if I go, there is my stack limit right there. And there is some advanced information. You can see we've got a whole lot of little stuff here, but basically you get your max memory size, max memory lock, things like that. This all really controls how much your application can use, and by default this is limited. So if you make a program that just puts trillions and trillions of objects on the stack, eventually it's going to crash and die. And that's why we have pointers to begin with. You have pointers, the heap, which is also called the free store, because you have basically an unlimited amount of memory at your fingertips. It's really not true. Some operating systems do actually try their best to limit, and some randomize it and do crazy things in the background. But when you think of the stack, think limited. You're talking literally like a stack of papers on your desk. You're only going to be able to fit so many on there. So now that we've talked about that, let's make a basic object and just play around with this. So we're going to make this, call it my class. It's not going to be any scientific discoveries here. This is going to be very simple. I just want something to show the full life cycle of an object. And let's go ahead and put deconstructor in here. And we're just going to say created. And this will be the point of contention with some programmers where I'm going to actually say this is destroyed. And they're going to go, whoa, 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 you haven't actually destroyed it yet. It's in the process of deconstructing it. It's not actually destroyed until it gets here. You're absolutely right, but I'm not going to argue about it. It's just we're going to say I want to know when it's created and I want to know when it's destroyed. By the time you see this on the screen, it's already gone. So let's play around with this just a little bit here. So what we want to do is say, my class create. Yes, we're going to actually create a class here. And instantly it's going to say unknown type. So, all right, let's figure that out. And looks like we can actually do something here. So we're going to say my class and my class boy, I'm screwing that all up. Set object name. That's what I'm looking for here. And we're just going to return this. Instantly we have a problem. What is this? Call to implement a deleted copy constructor. That's exactly what we were talking about previously. So let me pull this up here. Yeah, the queue disable copy. That's exactly what's going on. We're trying to creating something on the stack here, and then we're saying, hey, here's the object, but we're actually calling the copy constructor in the background. So we can't do that. This just simply won't even work. Super frustrating. Okay, so let's figure out a way around this. Your first thought's going to be pointers, and you're absolutely correct. We could do a pointer. But creating a pointer obviously detracts from our conversation about the stack, so we're not going to do that. First thing we're going to do is test the lifetime. And we can actually grab this guy and let's test this. What's really going on under the hood, and anybody who knows anything about even entry-level C++ is going, this is painfully obvious. We are creating an object on the stack, and then because it's going out of scope, we're destroying that object. That is the beauty of the stack, automatic memory management. Qute's royal pain in the behind is that disable copy, and you've got to get around that somehow, but it introduces some problems. And these are all what I would call stack-specific problems, but at the same time they can go into heap problems. And let's just show an example here. So let's say void mod class, and we're going to say my class pointer to this guy. Now we're going to take this guy and we're going to set the object name. And then we're going to basically say, all right, because it's a pointer, we want to delete it when we're no longer using it. What could possibly go wrong here? So probably help if we had the right class name in there. There we go. Let's run this, see what happens here. Uh-oh. It was created, it was destroyed, double free corruption out. What? Wait, what? We didn't copy it, so what's going on here? You guessed it. We actually treated that like a pointer and deleted it, even though it's living on the stack. So anything that's on the stack should not be deleted. Probably help if I could spell today. There are sometimes that rule's not really applicable, but by and large, when you're on the stack, you should not try to delete something. Let's try that again. Now it just works. And when we close the program, this will automatically be deleted for us. C++ 101, no brainer there. But you'll find this time and time again where somebody's going to say, hey, give me a pointer to this. You're going to say, well, I don't want to work with pointers. I'm going to give you a reference to it. And then they go, well, I'm just going to delete that because it's a pointer and it's no longer used. And then you can't figure out why your program keeps crashing. Super frustrating. All right, so what if we were to do something a little bit different here? What if we were to actually take this guy and say, give me a reference to him. See, now we're being a little smarter here. And if we try to do a delete later, what's going to happen? Let's see. Let's say mod reference. And I'm just actually going to shorten this to mod ref. So let's get rid of this. There we go. Now I don't have to worry about pointers or references to. I just say, here, do something with this, and then it's going to do something. Again, double free corruption because we're playing around with memory. We really shouldn't. So just because we're on the stack does not mean we're necessarily safe. Bad things can happen very rapidly. So the point I'm trying to drive home here is that the stack, as beautiful as it is not always perfect, and some bad things can happen very, very quickly. To make matters worse, we cannot copy an object due to that QDisable copy. So we're almost forced into using either pointers or references. Oh, that gets super frustrating sometimes when you're working with Qt. Now let's talk about the heap or the free store. And let's take a real deep look at this. And when I say deep, I mean we're probably going to break some things. So what is it? It's the heap. The description, it's the quote-unquote free store where you can allocate pretty much anything you want. You're free to do anything you want to do, but it comes with a cost. You control the memory management. And I have to highlight that because some people, yes, even in this course, are going to scratch their heads at that concept. I've had people go through my Qt Core Advanced series where they come back and go, can you explain what a pointer is? I'm a little lost. You should not be in an advanced class if you're struggling with what a pointer is. But anyways, why do you need this? Why is the heap even there? The stack works just fine. Well, the problem comes in, like we saw with QObject, sometimes you can't copy things. And because you can't copy things, you're almost forced to work with a pointer. Pointers are blistering fast. Think about it this way. You are a person. If I were to make a copy of you, think of everything that makes up you as a person. Your muscle, your bones, your lungs, your organs, your eyeballs, hair, everything, even your thoughts, feelings, your hopes and dreams, every little microscopic thing about you needs to be an exact copy, and that takes time. So to save time, rather than copying, what we do is we put a pointer, and I shamelessly stole this off the internet somewhere, that lives on the stack. This pointer points to something on the heap. And if you're in this course, you're probably rolling your eyes going, I know, get to the point. The point is, rather than making expensive, slow copies of things, you can just point to it and then point to a different one. And pointers can point to other pointers, and you can do some really crazy things. But going back to our conversation on design patterns, the more complex you make something, the more error prone it becomes, and pointers add an infinite amount of complexity. Whew. All right, so let's start this off by diving outside of Qt. We're going to say my class, not going to choose a base class, and I'm just going to hit next. This should just give us a normal C++ class. You notice how we're not inheriting QObject at all. Going to just put in some includes there so I don't have to waste a lot of time typing those out. And we've got our my class, and let's actually do a copy constructor. And I'm going to say const my class and old. We tend to take copy constructors for granted, and we tend to let C++ just copy like crazy. And doing that can lead to some really bad things, even if we're working with pointers. Just being overly obvious for anybody that really downloads this. Constructor, there we go, English 101. Now I'm going to add in a little private variable here. And I'm going to put a getter and setter in there. So very, very simple C++ class. There's really no magic to this, but we are going to do just some absurd things with this. So we might break our system. And if this does happen, well, I'm going to take a wild guess that it's going to be a bad alloc error. And what does that really mean, bad alloc error? It means the free store, bring up this graphic, is not infinite. We can't just create whatever we want. We can't create trillions of universes, although that'd be insanely cool. Eventually we're going to run out of memory. And the operating system is going to stop us at some point and say, hey, if you keep going, you're going to crash not just you, but all the other applications, including me, the operating system, so I have to limit what you can do. So you really don't even have full control over the heap. It's actually very limited in what you can do, even though it gives you the illusion that you can do anything you want. All right, to demonstrate this, we're going to, let's go back in here. I want to add another function. And let's say, I need a really good name, something that just screams I know what I'm doing here. Let's say void log. Yes, perfect. The best name ever. QString message. So what we're going to do is we're going to turn this log into just something that prints it out on the screen. And I might actually just do this object as well. There we go. So far, no little gremlins, but we're about to break some things really, really fast. So we've got constructing, and because we're constructing, let's go in and do our deconstructor as well. Constructing, destructing, and let's go ahead and say qint64. That's right, we're going to make something large. Limit is what we're going to call this, and we're going to say numeric limits of the qint64, and I'm probably doing this very, very wrong. I'm just trying to break this. And now I'm going to say, 64 max equals the limit, and I want to actually divide that by some absurdly large number. So really, what are we doing? We're saying, hey, standard library, give me the numerical limit of a qint64, which is just massive. Divide that by some massive number to try to like squish it down a little bit, just to see at what point we will actually break things. And then I'm going to say for qint64 I equals 0, and I'm going to say I is less than max, I plus plus. I'm just going to increment this here. Oh my goodness, what have I done? There we go. And let's toggle indent. There we go. Now it's all beautiful, and I'm going to say mdata append, and I'm just going to append one character. Could do this differently if we wanted to. Pad it with anything. I don't really care. And then I'm going to say log constructed. Ah, we are super smart. All right, we have outthought everyone who's ever worked with C++ in history. No, of course we haven't. We're not very smart. We're actually pretty much going to destroy this whole thing. So let's look at our copy constructor here. Not sure if this will even do it for us. Oh, it did do it for us. Sweet. All right, so we've got our copy constructor. Now what happens when we go to copy? Well, C++ comes in and says, take this object and everything it owns and try to copy it. But things are not going to work the way you think they are. So we actually have to manage the copying because we have this data. And we're just going to pretend that this is a more complex data type than what it actually is. A harsh reality is C++ will probably copy that with no problem. But we're going to take ownership of it. Why not? So let's go ahead and grab this little guy here. And we're going to say bang, bang. And let's say I is less than old data. So as long as we're less than the old data, then we're going to go ahead and data. And I'm going to go ahead and get this and say old.data. And I want the at I. So we're just going to do a bit of cloning in here. Uh-oh, why is this suddenly saying we have an issue here? Ah, I know why. Not left. Work with me here. Length, there we go. And then I'm going to log out that we have copied this. So really what we're doing here is we are creating a class, making some data. We have a copy constructor so we can make a copy of this object and the data will go with it into our copy. And we are just pretending this is a much more complex data type than what it actually is. And because we're destroying this, let's go ahead and say right now this is probably giving some of you old school programmers a real eye twitch. I mean, despite my horrible typing ability. Just because what I'm doing is absolutely absurd, and no one should ever, in the history of human beings, ever attempt to do this just because it's not a good idea. But now we're going to demonstrate why is this not a good idea. Let's go in here. We've made our non-cute. We're done with cute. You know, we've made our non-cute objects. We want to be able to copy something because we're super smart at this, right? And we have the full power of the heap behind us, so we can just make as many of these as we want. So we're going to test copying. And I'm just going to say qinfo object nothing too specifically horrendous about that code. And let's jump down here and let's actually create a blank object. And then we're going to test copying. Doesn't really seem like we're going to do anything that violates C++. We can build, everything builds, and if we go to run this, what do you think is going to happen? Look at this graphics here. We're going to create something on the stack, right? And then we're going to create another thing on the stack because we're making a copy of it. We haven't actually talked about pointers or heaps or the free store yet. It's taking a long time to create that copy is what I'm getting at here. Because that's a large amount of information. Eventually this will stop. There we go. So the point I'm making here is that copying is very expensive in terms of memory and time. We took an object, a large object, and then copied it. And if we ran that again, you see that constructing and constructed, which much faster than copying. All right, there's a lot that happens under the hood. There's reasons for that. Let's move on here. So what we're going to do now is we're going to test a pointer. And what I'm going to do is I'm going to actually just copy this right out of my notes. So we're going to test a pointer. We're going to say my class what's happening in C++ gives us an object at the memory location. Interesting. All right. Let's test that, and let's get rid of this little test copy here. So, much faster. We didn't have that nasty copy going on here. Now let's try address of. And we're going to just test address of. There we go. It's going to grab that reference right there. Bang, bang, run this. And same thing, just as fast as a pointer. There's no copy involved at all. Now, so far, we have been working exclusively on the stack. We've been using pointers to and references to things on the stack, this little guy here. We haven't actually moved anything off the stack yet. And this is a conversation about the heap. So let's actually do something here. Let's say void test. I'm not sure what to call this. Test heap. Why not? Now I'm going to say my class new my class, and then when we're done, we're going to go ahead and delete this. That was moderately embarrassing. There we go. All right, so nothing too fancy. What are we doing here? We're just going to do it on the heap, and we're going to say hello. A lot of people think that if we do something on the heap, because we're working with pointers, that it is faster. And, well, sad to say, it is a little bit faster, but it's not as fast as you would think. So let's do this. We're going to create another guy here. And here's where somebody's cringing and going, no, wait a minute, you're going to copy this. And actually, I'm going to do this in an entirely different function. Just a test copy pointer. There we go. This kind of does reach back to C++ 101, and I'm sure a lot of people have probably rolled their eyes and go, I know exactly what's going to happen. But there are some of you out there who are probably struggling with this, right? So I'm going to say, what's happening right here? We are making a copy, but what are we making a copy of? We're not making a copy of this class, we're making a copy of the pointer. Let's demonstrate this, just so we can silence all those naysayers who's going to go, no, this is going to take just as long as if we were making a copy. Watch this. Bang, bang. Fast. So, why did that go faster as opposed to an actual copy? So like if we run copy again, you can see how it's taking a very long time, and it's taking an absurdly amount of long length of time. I don't even have words. It's just taking so long. There we go. Because copy is extremely slow, and that's why they really try to force you in C++ land to work with pointers, because it is so much faster. Now we're going to test copying a pointer. Bang, done. Much, much faster. So what's really going on under the hood here is we've created an object out on the heap in this test copy pointer. And then we've created another pointer on the stack that's pointing to that same object. So it's much faster because now you're not copying all that data, you're just copying the little pointer address. So seems very rudimentary, but I had to put this video in because some people are going to sit here and argue that, the heap is faster, or that pointers are faster, or that using a pointer somehow magically means you're no longer copying, and it's just simply not the case. Okay, the last two videos probably seem pretty rudimentary, but I had to put them in there for a reason. We need to manage memory, but we should manage that memory in a way that Qt expects us to, or I should say that Qt wants us to. Now, you can absolutely manage it using the standard library in the C++ way, but Qt has some built-in utilities that make it super simple. So what we're going to cover in this video are memory leaks, stale pointers, and things of that nature, and how easy it is to do this. Now remember, we cannot copy a Qt object, therefore we're pretty much forced to using pointers at some point, and, well, pointers come with their own complexity and headaches, as we're about to see. Let's go ahead, add new. We're going to make a class, and my class, Qt object, next, finish. Probably going to copy and paste the bulk of this just because why not? Nothing super special about this class at all. Just going to go constructed and destroyed. Want to just see the life cycle of this object, and to save a little bit more time, I may just reuse this class over and over again. All right, now we have a simple Qt object. We can take this Qt object and do things with it, but because it's a Qt object, we cannot copy it, so we're forced to work with pointers, everybody's favorite, right? So let's go ahead and say QList, include QDebug, and include my class. We're going to make a very, very common issue. Fill list. So what we want to do here is we want to say QList my class. Now we can't do this because it's a Qt object. We can't copy it. So now we have to work with a pointer. Super frustrating. So now we've got a list, and we're going to say int max. So really all we're going to do is we're going to create a list of pointers. All right, so pretty simple code. Not going to win any awards for this, obviously, especially with my horrible typing skills. Notice what we just did. We used a very, very bad word, new. Anytime we use new, we are creating something on the heap, and, well, now we have to manage this. We created it, we own it. So now I'm going to say set object name, just so we can see what we're doing here. Now we've got some pretty descriptive objects. We need to just say list append, and we're just going to put that right into our list. Seems simple, seems easy, but what's wrong here? Well, we created these pointers. Now they live in this list. Oh, that means we have to manage this list memory. Oh no, that's right. So what we're going to do now is we're going to demonstrate a memory leak. And we're just going to say QInfo can get rid of that, and then we can say fill list, and we want our list here, and we just want to do 5 of them. Nothing horrendous. And then we want to do some stuff. Actually, you know what? I don't want to do that just yet. We're going to back out of here. What we're going to do next is we're going to say clear. Very simple. I want to make sure this is crystal clear before we move on. But what's happened here? That's right. Clear does not automatically delete these pointers. So we're just going to run this, and we can demonstrate this really, really simply. Remember, our class very simply is going to say constructed or destructed. So when we run this, because we're constructing them, we'll see they're being constructed, but we never get rid of them. We never delete them. See? Constructed. Never called the destructor at all. So those just live in memory. And this has actually gone out of scope already. So they're just living in memory. And well, now because we don't even have the pointers to them, we have no real way of accessing those. So these are just living out on the heap. Now, most modern operating systems, and I have to say most, will track what memory this application is creating. And when the application closes, they'll go out and try to free that memory up. I stress try to free that memory up because it's not really a guarantee. As the programmer, we create it, we own it. So why is a memory leak so bad? Because you have a very short amount of memory the operating system is going to give you. So if we go, there's our stack size. And I'm on Linux, so it's just ulimit. On Windows and I think Mac, it might be a different command. But basically, you can Google how to get your stack size. Stack is, well, the managed store, the stack. The heap size, well, that's a little bit different here. You have to look up the specifics for your OS to figure out how much memory you're actually allowed to have. There is an actual upper limit. Most operating systems, even though the heap is just your RAM, it's not going to give you all of your RAM. So if you have, say, 32 gigs of RAM, you do not actually have access to all 32 gigs in most cases because other programs need that. For example, your operating system. So how does all that work? That is a mystery that shall remain, unfortunately. I can't go into detail on every single operating system and what's going on under the hood. And some operating systems do actually contradict what I just said. They will give you as much memory as you need. Anybody who's ever worked with like SQL Server on Windows know that if you run the SQL Server, it will just take literally as much memory as the operating system will give it, even if it doesn't need it. It's extremely frustrating. So eventually, your program will leak enough memory that it will crash. So I'm going to actually call this demo dangling pointer. And what we're going to do now is, you guessed it, we're just going to create a dangling pointer. We can pretty much just grab this. I was going to kind of combine both of those into one, but I want to really detail this. Creating dangling pointers, so we've got our list. We're going to get rid of this, and what we're going to do now is we're going to say, yes, you know what? I want to delete some memory. And I'm going to just say delete list.at, and I want to say 2 because I don't need that anymore, but I forget to actually delete it out of the list. So what's just happened here? The memory's gone, but that pointer's still in our list, because remember, the pointer actually does not live out on the heap. Ooh, that's scary. Where does the pointer live? It lives on the stack. So the pointer is going to point to something on the heap, even though it lives on the stack. Uh-oh. Yeah, you see some danger here. All right, so let's get this. And now let's say, very, very simple, for each my class item in list, and I'm just going to simply say QInfo item, and I want the object name. Let's see what happens here. Dangling pointers are extremely deadly to a program. I don't want to be overly dramatic, but I can't even tell you the number of times somebody said, hey, can you tell me why my code's not working? And this is why. Blop. So what just happened here? We constructed some objects, we intentionally destroyed an object, and we still have 5 objects in our list. 1, 2, 3, 4, 5. Even though we destroyed one, we never removed it. So we get to the 0 position, the 1 position, and on the 2 position, whoop, that's right, our program just went boom. So I realize this is a bit of C++ 101, but now we need to actually manage this memory, and we should manage this in a way that Qt wants. So I'm going to say demo correct. We've been working with a list, so I'm just going to continue on with this list here. And what I'm going to say is, now that we have this list, I want to call Q delete all. And what this will do is take a container and delete all the pointers in that container. This can be very deadly if you don't actually have pointers in there. But then I'm going to say list clear. That will do 2 things. First, it frees the memory. I shouldn't say freeze, I should say deletes the pointers, and then removes the dangling pointers. Now, maybe I shouldn't say delete the pointers, deletes the memory, and then removes the pointers. Now we can simply take this same code, and it's pretty obvious what's going to happen. This should just work without any problems. Ta-da! Now we've got constructed and destroyed all 5 of them. Beautiful. I should probably change this make dangling pointers, but you get the point here. This thing just works beautifully. We are now doing this the Qt way, and the focus here is the Q delete all. That little guy will save you a lot of headaches. Now, you could have very easily gone in and said for each delete the item. But you are really at risk here of running into a dangling pointer, and then you could crash your program. When in doubt, trust this Qt delete all to just wipe out everything in that container, and then you are responsible for clearing out those dangling pointers. I almost wish they had baked right in here, like put an optional, like, clear list for true or something like that. It'd be a lot cleaner if it was all in one line. Now we're going to look at parent-child memory management. This is what really is, I would call, the Qt way of doing things. And it's pretty basic. We probably covered this dozens and dozens of times in Qt 101, but I have to include it here simply because it is so baked into their design pattern. Parent-child memory management is AKA the Qt way. If you're doing something other than this, you need to really ask yourself why. Why are you deviating from their super easy memory management? I've got my class in here, and it does exactly what we think it does from the last video where it just says constructed or destructed. We just want to see the class's life cycle. Let's go ahead and dive in here. And let's go ahead and include the my class. And I'm going to create children here. So I'm going to say void and this is where things get a little bit interesting, because I want to say my class, and I can do a pointer, or I can do a reference to, I'm going to do a pointer, parent. And why am I doing a pointer? Because that's typically what you'll see out in the Qt documentation. I don't want anybody getting super confused, but because we're working with a pointer, we probably should make sure that pointer actually exists. All right, now that we have a pointer to our parent, we can do pretty much anything we want. So I'm just going to say for int I equals 0, I is less than the count, and then I plus plus. And I'm going to say my class child equals new my class. Notice how it says QObject pointer parent equal null. So by default, that's going to be a null pointer, and I want to actually say this is our parent. What happens here is a few things. First, we have a pointer. Second, we have a parent. That parent now assumes memory management of that child. So when the parent's destroyed, all of its children are destroyed with it. It's kind of like a sick horror movie if you think about it. The parent's like, if I'm going to go, I'm taking all of you with me. And it's kind of a morbid way to think about it, but it really is kind of how that works. So I'm going to say child. I want to set the object name, and I'm going to say child. Nothing really super complex about this. You've probably done this code hundreds and hundreds of times. So we're going to take this create children, and we're going to actually work with it here. So I'm going to say testing the cute way. First thing we're going to do is we're going to make a parent. So I'm going to say my class parent. Going to give it a null pointer, and let's go ahead and call this the ever descriptive name of parent. So now I'm going to call create children, and I'm going to say parent, and I want to create 5 of them. You have 5 children. Now, if you have 5 children, you've got bigger problems. Probably money issues would be my guess, but neither here nor there. Let's go ahead and just test this out. Notice a couple of things right off the bat. First, the parent here is on the stack. These are on the heap. But let's go ahead and run it and see what happens here. Sure enough, we've created that, and then we have created all these children, and then we've destroyed the parent, and because the parent was destroyed, all the children were destroyed with it. That is extremely cool. That makes memory management so much easier. And again, I'm almost ashamed to even put this video in here because you should already know this if you're working with Qt. But just in case you've skipped beginners, intermediate, and advanced, and you somehow here, this is how the parent-child memory management design pattern actually works. And if you're not doing this, stop, ask yourself why. This is the Qt way of doing things. Now, the other problem we end up having is, now that we have children, how do we interact with those children? Well, let's play around with this a little bit. I want to list my children, all 100 trillion of my children. All right, so I want to say my class parent, and then I'm going to say if not parent, return, and I'm just going to grab this. I'm going to list those kids out. And this is where I'm going to say simple for each. Ta-da, there we go. Now, you know something right off the bat. Cannot initialize variable type my class. What is going on here? You might have run into this and said, hey, I don't understand what is going on. What happens under the hood when you add that child in there? It gets cast as a QObject. So now we have to do some casting. Suddenly, now it says, oh, I know exactly what you want. Oh, that's frustrating. So now what we should do is say QObjectCast, and I want a my class pointer to obj. Now you should probably put some like test to make sure we have a pointer. But just for demonstration purposes, I know this will cast just perfectly fine. QObjectCast is how you would say, I know this is a QObject and I want to cast that from one QObject type to another. So because our child, ta-da, is a QObject, we can use that and it works just beautifully. So we've got create children, we're going to list children. All right, so listing children, and then there is our children in all their glory, and then we're go ahead and we're going to just destroy them. So now we can access individual children in there. I want to take this just one step further, and I want to try to find children. So let's go ahead and say find children. I should say find child. What we're going to do next is we're going to say, let's find a child, one specific child in that list of children. So again, we can just simply say, all right, let's do this. QList. Now, if we try to do my class, we're going to get an error. So let's say QObject pointer. And then we're going to say parent find children. And we say find child, but I'm going to do find children just in case there's more than one. And then I want to give it the name. So you might be scratching your head going, whoa, 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 what's name? Why are we asking for a string? Well, if we look up here, set object name. So what we're really looking for is child and space a number. So we're going to get back a listing of children. And that's why I wanted to do find children, just in case you name multiple objects with the same name. They're independent QObjects. They can't be copied, remember. They're independent QObjects, but you can name them the same. So now you can have multiple objects with the same name. You can have two children named Bob or two children named Alex. All right, now that we've got our list of folks here, we can just say bang, bang, let's grab this. And we're going to go ahead and just cast that out, and there's our child. And we're going to say found. Makes it super, super simple to work with children. All right, so in here, we could list the children, and then we're going to say find child. And I want to find child 2. Save and run. Let's see what this finds. So we found one child, and there is the child that we found right there. And everything works beautifully. We don't have to worry about memory leaks. We don't have to worry about any dangling pointers or anything of that nature. It just works as expected. Okay, we're going to talk about resource acquisition is initialization. And what does it really mean? And while you can read this whole thing, shorthand, what it means is allocation is done during the creation of an object, and resource deallocation is done during the object's destruction. So when you create an object, you gather the resources. When you destroy the object, you release the resources. And let's look at a pretty solid example of that. See, solid example, no pun intended. or was there a pun intended? Anyways, so we're going to go to a console app. We're going to say Qt5 design patterns, and this is 4-5. Bang, bang. And just going to put some notes in here. And it says it makes it easy and Qt follows RAII mostly, not all the time. So we're going to make a simple server. When I say simple, there's actually not a whole lot simple about this. If you're a beginner, this is going to make your head explode. Just fair warning. So we're going to add in networking. And I want to actually put that in my notes. Because sometimes people will download this code and they'll not understand why it doesn't work. So we have got our main file, and we're going to actually make a multi-threaded TCP server using a thread pool. Whew, say that after a few cocktails. Okay, so because we're going to be working with the thread pool, we need to kind of do things a little bit differently. And we're going to go add new, and I want to add a class. And I'm going to say my connection. And in our connection, we're not going to make this a Q object. We're just going to have this as a normal C++ class. And now we're going to add a new my server. And this, of course, will be a Q object. Now, there's a reasoning behind this. It just makes it super simple. And the connection is going to be a Q runnable. And Q runnable is not a Q object. What? Okay, so think of it in terms like this. The connection is the actual connection, the TCP connection. We're making a wrapper around it to handle that thing. So I pasted some includes, Q object, Q runnable, the socket, debug, and thread. So yes, we're going to be working with sockets and threads in this video. And right here, we're going to just say Q runnable. And if you've worked with thread pools before, you know these things are pretty sweet. We're going to add the run function. So what happens under the hood is you'll create a runnable, you'll hand it off to the thread pool, and the thread pool will call run in the background here. And when we call run on this, it's going to actually be on a separate thread. So pretty cool how that works. I'm going to get rid of that little guy there. And I'm going to say, why does it say public? That's annoying. All right, so we're going to say void handle, or actually let's do set handle. You know, there's probably an easier way of doing this. Sometimes I just like to argue with the editor. I don't know why. So we're going to say socket, and we're going to make a pointer called msocket, maybe. There we go. And then we're going to make a q int ptr called mhandle. And then we're going to create a getter and setter. Now, notice this has to be a pointer. Q object, and there's a reason for this. I'm just going to paste my notes right in there rather than try to type all that. Q objects cannot move threads easily. And what I mean by that is if you create an object and then you try to move it to a different thread, which you've probably done hundreds of times, sometimes that doesn't work too well. So you get what's called a cross-thread operation. Q object cannot create children for a parent, keyword parent, your parent-child hierarchy, on a different thread. So if you have threads A and B, and you try to create a thread on B with a parent of A, bad things happen. Seems super confusing because it is super confusing. Let's switch over here, and let's actually flesh this out. And we're going to just go right here. I'm going to say Q info. Whoops, don't know why I even did that. And Q thread. We want that current thread. So we want to know what thread we actually did it. do not create the socket here. We're talking about RAII, but you would think, hey, we're creating this, we should create it here. No, do not do that. Why? Because this will be created on the original thread with the parent, and this is going to be shoved into the thread pool as a separate thread. Oh, that gets frustrating. So now, because we're working with RAII, we need a deconstructor as well. Now, somebody out there is probably screaming, well, if you're not doing it here, it's not RAII. The shorthand version of RAII is that you use the resources, or you create the resources when you need them, and you get rid of them when you no longer need them. You're not holding on to resources through a full object lifecycle if you don't need them. And we're going to demonstrate that. So I'm going to say, just grab this guy. So we destroyed that, and I'm going to say if msocket. So if we have a socket, we're going to say if msocket is open. We're going to go ahead and close that. And then we're going to get rid of that socket. So super confusing. Is this RAII? Yes, and here's why. This may be the constructor of the class, but this is when the class actually gets run on a thread. So this is where the execution starts. Gather the resources here. And we're going to say execution ends, release the resources. This is why RAII gets a little bit confusing, because you're going to be inclined to do it here, and you really shouldn't, because we're going to have a cross-thread operation that will completely break this thing if we try to do it some other way. All right, so I want to add in another little guy called handle connection. And then I'm going to right click and bang. There we go. I'm going to move this right up under here so we can see very easily what's going on. So when run is called, this is what we need to really focus on here, is we're going to start running on a different thread. And that's why I've got this current thread, because you'll see when we run this how that thread is going to actually change. Now we need to do our RAII, meaning we need to actually create that socket. And now we've created a pointer. This is kind of the pain part here. Because we're working with a pointer, now we have resources we need to track. This gets super frustrating. And we're going to set descriptor. There it is. And we want to get the mhandle, which we're going to set when this thing is created. And we are going to wait for disconnect, or actually wait for connected, sorry. Wait for disconnected. We'll be there a while. And then we're just going to handle the actual connection. So when this is run, this is going to be on a separate thread inside the thread pool, and then anything that we call is also on that separate thread in the thread pool. That's kind of why I broke that up, so you could see that, hey, anything you call on the thread stays on the thread, unless you specifically try to move it off, at which point it may explode. All right, now we're going to handle this connection. We're going to say q byte array. And let's call this data. and I've got some code. I'm just going to the old copy and paste, bang. We're going to just say data append hello world. We're going to write it. We're going to wait for those bytes to write, and then we're going to close that socket. At which point, the runnable has nothing to do, and the thread pool automatically will delete this because we're going to set this to auto delete, which means it's going to come up here on yet the main parent thread, and it's going to release this bad boy, and that socket's going to have to be deleted. So there's our full object lifecycle for that socket, or RAII, is it starts here in run and ends in the destructor. Again, we didn't do it here because we'll have a cross-thread operation, and it's going to get really ugly if we try doing that. Whew, super confusing, but that's why I'm doing this example and not a very basic class, because someone somewhere will try this and then wonder why they have all sorts of issues. So let's go into our server. Just going to paste in the includes. We have in order QObject, QTCP server, QThreadPool, QThread, QDebug, and our connection class. All right, so let's go into slots, and I'm going to say void, and I want about to quit. And now we want to actually go in here and say QTCP server, because we are making a TCP server. And now we need to handle this incoming connection. And again, this is very error prone depending on what version you have, so always trust whatever type it's putting here. If you ever have an incoming connection that never fires off, that would be why, is the type is wrong. This used to be like a QINT64, an int or something like that. So as they've moved from one version to the other, it's gotten a little bit finicky here. I'm missing our about to quit. There we are. All right, so our server, super simple. We're going to just kind of dumb this down just for the sake of time, or we'll be here all day. Closing the server, and we can go ahead and close this. Not sure if we're even going to use that. I just want to add that in case somebody downloads this and decides they want to use it. So we're going to go ahead and make our runnable my connection, and let's call this client. Oh, memory leaks everywhere. So I'm going to actually put in danger, no pointer, or a pointer with no parent. So why are we doing it this way? Because if we try to set the parent, we're going to have some sort of cross-thread operation. Frustrating. So this is how we do memory management for the thread pool. We're going to say client set handle. That way we can get the handle of the incoming socket connection. In case you're really super curious what that is, it's just a number. The OS says, hey, here's a number, and it may be like 1655, 255, 6000, whatever, of whatever socket on the underlying operating systems that's sitting there waiting for the connection to be accepted. But now we want to do our memory management. So we're going to say set auto delete true. And I believe this is true by default, but I simply don't trust it. So I always set auto delete true. Then QThreadPool, and I'm going to say global instance. That's right, every single app has its own global instance. And I'm going to say client. So we're going to start our runnable. And I'm going to just copy and paste in some notes. So if somebody downloads this, they're not completely clueless what we're doing. So in order, incoming connection fires off from our server. We make a client, but we are in danger because we have a pointer with no parent. So we need to manage that memory. We're doing that here when we're telling the thread pool to take ownership of that and delete it when it's done. And then we're just saying, hey, set that handle. So inside of our actual connection object, when we run, we can actually set the socket descriptor to the handle. So we tell the underlying OS, hey, you gave me a number of 55. I'm going to go ahead and take ownership of that socket, and I'm going to now read and write the data out of that socket. If that seems confusing, it's because it is. Socket programming's always been a pain for just about everybody everywhere. So let's jump back in here, and now let's make this thing actually work. So we're going to say include QObject and include my server. Need some screen real estate here. There we go. And I'm just going to say my server. And let's go ahead and call this server. And now we're going to simply connect signal and slot up. So I'm going to say QObject connect. And I want to connect to this QCore application. And I'm going to say I want the QCore application about to quit. You were wondering where that was coming in. Okay, so now when the application is about to quit, we're just going to simply shut that server down. So we're going to say server, and we want the my server about to quit. So when the app stops, the server stops. Otherwise, this thing may hang in the background indefinitely until we force it to stop, and that gets super frustrating. If not, server. And I want to say listen, and I want Q host address any. You can change this to whatever you want on your operating system. And I'm going to do 3372. Again, pick a port that's not in use and isn't going to piss off somebody's virus scanner. And I'm going to say server dot error string. In case you skipped it, I did have a video that I made where I used a port, and I had no idea at the time, and the port was known to be a virus port that a common virus used, and I didn't even know about it. And so somebody said, hey man, you infected my system. I typed the code exactly as you typed it, and now I have a virus. And I had to explain to them that's not how this works. All right, so our server in all its glory, let's give it a good build, make sure we didn't screw anything up because that was a boatload of typing. And there's a whole lot of scanning and stuff going on. Let's do that again just to make sure. All right. And listening. All right. What port did we do? 3372. So I'm going to pull open Telnet. And all right. There is our full socket lifecycle there. So listening, and then it was constructed on this thread, and then it was constructed on this thread, and there is our actual client right here. And then constructed everywhere. Let's redo all of that. I got a feeling I got a little copy and paste friendly. Destroyed, yes. Not constructed running. Constructors everywhere. That's embarrassing. Super easy to fix. All right, let's try that one more time. So it is now listening. Let's pop, where are you? There we go. Didn't want to work with me there. So we're just going to telnet into that server, and that should be a little more easy to understand here. So we have constructed on this thread. We are running on that thread. It is now pooled. We're handling that connection, and then we're destroying. So there is our full object lifecycle. Now, the whole point of this isn't really cross-threaded TCP server operations. The whole point of this is RAII, resource acquisition is initialization. And what that simply states is create the resources when you need them, destroy the resources when you don't. And they take it a little bit kind of a written in stone approach where they say resource allocation is done during the object creation by the constructor, while resource deallocation is done during object deconstruction by the deconstructor. But this is an example of when you simply cannot do that. If we were to go into our connection and create the socket here, we'll get a cross-thread operation. So we simply can't. So we do it at the earliest possible point, which is when the thread starts or the execution starts. This video we're going to talk about QScope pointer. It's a smart pointer in Qt that, well, does exactly what it says it does. It only lives as long as it's in scope. So as soon as it goes out of scope, it automatically deletes the pointer that it has inside of it. If you know QScope pointer and you're an expert in this, go ahead and safely skip this video. But if you have any questions or concerns, pay attention. So we're going to jump in here. We just have a very simple class, which admittedly is extremely simple. We're just going to monitor the life cycle of this thing. And I'm going to put in a QString and a QString. Switch back here. And through the magic of copy and paste, we're just going to go bang. So I'm not wasting a lot of time here. So really, when we create this class, we're saying, hey, give us a name also, and we're just setting the object name. That way, when we print out this, it will say the name of the object. So we can name it whatever we want. And we may reuse this class in future videos. But it's just constructor, deconstructor, and a test function. Not super, super complex. And now we're going to go in here, and let's just add in some includes. QDebug, QScoped pointer, QScope pointer array, and the my class, which we just created. So without further ado, what are we going to do here? We're going to say my class. We're going to break some rules is really what we're going to do. And we're going to say make class. This is going to be horribly misspelled, but we're going to just say, for example, this is some library that we're talking to. A lot of libraries do this where they'll say, here, I'll just hand you a pointer and you now own it. Oh, that's frustrating when they do this. You'd be surprised how many applications in lib do this, even though now we have potentially a dangling pointer out there. So we're going to say return new my class. And this is a null pointer. And let's go ahead and give it a name as well. And I want to say so this is just some library or some code somewhere that we're interacting with, and it's just handing us a pointer, and now we have to take ownership of this pointer. And this is where QScope pointer really comes into play here. So we're going to say test scoped. And we're going to take ownership of the pointer. We can take ownership as soon as we get it. So we're going to say QScoped pointer. This is a typed, so I'm going to say my class. And let's call this P for pointer. And then we have to actually give it the pointer. In this case, it's the make class. And let's call this my smart pointer. Some long, obtrusively long name. And notice how we don't have to mess around with, hey, there's no star in here or anything like that. It's not like this. We're just basically saying, create a QScope pointer of this type and give me the pointer. That's all we're doing. Now, from here, we can do whatever we want. And this is the really cool part, is we don't have to say like pdata.test. We can actually just call that test function directly and just treat this as if it were just a normal pointer. That is insanely cool. We could also, if we wanted to, access the raw pointer itself. For example, we can say my class ptr equal p.data. Oops. And that gives us the pointer to the class. However, typically you don't want to do this because now you are in memory management land. And that's the whole point of this, is we don't want to have to even think about this pointer. So what happens? How do we delete this pointer? Well, it's a smart pointer. So once this goes out of scope, this guy right here, once it goes out of scope, everything is removed automatically. It's so cool. I love automatic memory management. Don't even have to think about it. So let's go ahead and test this. Save and run. And you can see constructed, test called, and destroyed. So we have our full object lifecycle right there, and we never had to delete anything. It just does it automatically. That is so cool. Now, as with almost all of our videos, we're going to take this to a more difficult realm than the simple this is a scope pointer. So we're going to actually test an array of scope pointers now. So we're going to say void test scope array. And let's go ahead and we're going to make an array of smart pointers. And we're going to say we want a maximum. And let's go ahead and say Q scoped pointer. Q scoped array pointer. Boy, that's a mouthful. I wish they'd shorten that. My class. In case you're wondering where I got that from, it's from the includes that I copy and pasted up here. And Q scoped array pointer, you guessed it, just holds pointers in an array. It's really not rocket science here. A little bit different though. So we're going to say here, and we're going to say p dot reset. So we just want to force one in, and we'll say new my class. Max. So we're going to initialize our array. Now we don't really play around with arrays too much in Qt land, but in normal C++ land, arrays are like all the rage. They're the snazzy thing that everybody likes to work with. And that's why this class Q scoped array pointer exists, because we want to actually work with an array of pointers. So for int I equals 0, I is less than max. And then I'm just going to say p I equal, actually, let's say test, because it should already be in there. And then again, when it goes out of scope, everything's removed. Let's go ahead and test this, and let's grab that. Save, run, and let's see if this works. Sure enough, we had a whole bunch of constructed, a whole bunch of tests called, and a whole bunch of destroyed. So our automatic memory management is working as expected. That is just insanely cool. So if you ever have some C++ code like from a library or somebody's class and they're handing you an array of pointers, this is how you would really tackle that. All right, so let's go ahead and do a smart list cleanup. And let's say, I have to explain this a little bit. So with the QScope pointer, we can actually determine when we delete, when this deletes, we can actually make our own function and determine what happens when it's deleted. And that's really what we're going to do right now. So we're going to say, this struct calls the myCustomDeallocator to delete the pointer. And that makes 0 sense at the moment, but bear with me. So we're going to say struct, and I'm going to say smart list cleanup. So we're just making a struct. And I'm going to say static inline, and I'm probably doing this horribly wrong. Somebody out there is probably screaming at their monitor saying, no, there's a better way, don't do it that way. And inside of our inline function here, I'm going to say QList myClass. And this is going to be a pointer to a list. And then I'm just going to call Q delete all. And then we're going to clear that list out. Probably a vastly simpler way of doing that. So now that we've got this structure with our inline function, what are we going to do here? Well, we're going to make a custom deleter. So let's go ahead and go void test custom deleter. And there we go. Test our custom delete. And I'm just going to comment this out real quick. All right, so now that we're here, we're going to say QList my class, and it's going to be a pointer. And I want a QScope pointer. And this is where things are going to get a little weird. I'm going to put those in there so you can see you need to have this, because this kind of screws people up sometimes. QList, and then again, my class. And now we want to give it our custom deleter. In this case, it's going to be the smart list cleanup that we just created up here. QScope pointer, say that 5 times real fast. QList pointer my class, and then we're going to call a custom deleter. Whew, man, that is confusing. All right, so P, and let's give it the list. Wow, that is a handful. So, and we could actually put some sort of like, you know, we're going to delete or something like that. We could say like QInfo. That way people believe this actually works. Let's just call it custom cleanup. There, we're more professional now. Marketing's going to love us. Custom cleanup. All right, and then we're going to say for int I equals 0, I is less than, I'm just going to pick a number 10, I plus plus. And let's say list.append, and we want the trusty make class because we're going to get a pointer, and I'm going to say list. Got to give this some special name. It's got to be a name that everyone's going to know and love. QString number, and we're just going to do I. So we're just making a list of pointers. Nothing super special about that, and we can do stuff with our list. So for example, we could do a for each, and let's say my class. And then I'm just going to say item test. So we can just, you know, interact with those pointers as we need to. Now, here's the interesting bit here. This list, as long as I didn't screw something up, automatically clears and deletes the pointers because we have this smart cleanup here. So if we look at QScope pointer, ta-da! Let's go up, up, up. So QScope pointer, type template, type name T, type name cleanup. So that's really what we're calling is our cleanup function. It's actually really cool that you can do this. So then if you had some custom scenario where you wanted to go in and deallocate other resources, like you're using RAII or something like that, you could go in and actually do some custom code. You're not reliant on Qt to do it for you. So let's go ahead and test this. Assuming I didn't screw up any of the typing, bang, there it goes. There's our custom cleanup right there. So we have a bunch of constructed, a bunch of tests called, and then wham, automatically destroyed through our custom cleanup. Pretty cool. The last video we talked about scope pointers. The problem is a pointer's meant to be shared. That's the whole point of pointers. Get it? The whole point of pointers. And sorry, I won't quit my day job. Anyways, a shared pointer or a QShared pointer is a Qt smart pointer class for a pointer you intend on sharing with others. And this example will probably hurt some people's feelings and maybe even hurt their brains. I know it hurt mine when I wrote it. Let's just dive into it. So basically, we're going to make a pointer and we're going to share that pointer with other objects. And we're going to say 4-7. Got some notes. There's going to be a whole lot of copy and paste action here. All right, so what are we doing? Shared pointers, pointers that auto-delete when go out of scope. But we're talking about shared. Now scope, we're loosely defining this. So we should change scope to when no longer used, and instead of but, and can be used more than once. So I changed the official description a little bit here, but I think you get the point. So let's look at how we would actually use this. first things first, we're going to make a my class. I know, our infamous my class here. And we're going to go into my class, and I'm going to just copy and paste some includes in here. Bang. QObject, QDebug, QThread. Ah, see, you slowed down. We're going to do some threading. And QMutex. Ooh, mutexes are often confusing. I personally don't like working with them because I always screw them up. As I'm sure many of you know who you are, do as well. Alright, so we're going to right click, add our deconstructor in here, and then we want to just add some stuff. So let's go down here. I want to add an int mcount and our QMutex. And I am probably going to screw this way up to the point people are going to be like, whoa, that's not how you're supposed to use a mutex. I'm going to say add count and QMutex. All right, so let's go ahead and add that in. Add this in. And add this in. It would be super cool if you could just like grab all of these, right click, and then add them all in, but it just won't let you do it. All right, so inside of my class, this is where we're going to just rip out some copy and paste. So we're going to set the count to 0. We're going to say this object's been constructed on, and then the current thread. Nothing super special about that. Same thing with our deconstructor, final count, whatever it is, destroyed on whatever the current thread is. And then our count here is just going to return the mcount. The add count, this is where I'm going to actually type. We're going to say QMutex locker. I'm going to call this locker. Again, this is not a beginner's class, so if you're going, whoa, explain the QMutex locker, I did that in the advanced series. So QMutex locker is just going to take that mutex and lock it. I'm going to increase that count, and then I'm going to say, through the magic of copy and paste, bang, count is the count on whatever thread we're on. Wow, we screwed that all up, even with the copy and paste. And then our super snazzy mutex here. Did I say mutext? I did. Wow, that's embarrassing. Let's go fix that real quick, or it's just going to bug me. There we go. All right, so let's give it a good build, make sure everything's lining up. And if our copy and paste and typing skills worked and the sun, moon, and stars all align, everything should just work. Now we're going to make a runnable, and we're going to put this class inside the runnable. I'm going to say add new, and we're going to say class, and this is going to be a my runnable. Usually when you have a runnable, it's not really something you want to advertise to the world. It's a little bit embarrassing, especially if you're in public, but you know, we're coding, so why not? And we're just going to paste a whole boatload. It includes QObject, QDebug, QMutexLocker, QThread, QRunnable, QSharedPointer, there it is, QRandomGenerator. I love this class, especially for testing, because it just makes random numbers. And then our my class. And from here, we're going to, you guessed it, implement the runnable interface here. Bang. And because this is super annoying having two publics in a row, I'm just going to do that. And I'm going to say Q, and I want shared pointer of my class type. Let's go ahead and right click, add that in, switch back, and let's go ahead and set the pointer. It probably could have done this using the GUI, but sometimes I just want to slow down and explain things a little bit here. So we just got our getter and setter. And then we can literally just take this and then copy and paste. So what's really happening here, and this is why I want, instead of doing this and then right-clicking and adding, getting, etc., I wanted to slow down and really explain this a little bit here. So what we're really doing is we have a private variable of a QSharedPointer, which is of, or I should say, going to hold the type of a myClass. We have our getter and our setter, meaning we are now sharing this pointer. We're passing it around, and there are pointers everywhere. It's kind of like watching Oprah Winfrey. Pointers, you get a pointer, everybody gets a pointer. So in our run, we're going to say for int I equals 0, I is less than 10, and then we're going to just simulate some long activity. And then I'm going to say int ms equals q random generator global bounded, and I'm going to say 0 to 500, so anywhere between 0 milliseconds and half a second. I'm going to say the Q thread, the current thread, I want to actually sleep. You know, sometimes you just want to take a nap. You've had a long day. You just want to lay down and go, I'm done with today. And I'm going to say end pointer, and then we can just say add count. We could have done end pointer data add count, but this is just more convenient. And then in here we have our getter and setter. So we're going to say return. All right, so let's give this a good build. Make sure we didn't screw anything up. So far, so good. Now we have our class, we have our runnable. Let's go ahead and push this off onto a thread pool somewhere. Now, when we run this, we're going to have to make sure that we have set this pointer first, meaning this pointer, this QSharedPointer, is going to come from somewhere else. So we cannot use QScopePointer, or it would have gone out of scope. We would have to hand a pointer to a QScopePointer, which wouldn't make any sense. That's why QSharedPointer exists in the first place, because we're going to just pass this thing around, and in doing so, it would go out of scope. Whew, that's a mouthful. All right, let's flip back to our main here. Magic of copy and paste. I love copy and paste. Best invention ever. QDebug, QThread, QThreadPool, QSharedPointer, our class, and our runnable. Let's go ahead and build out our test function. And before we get any further, I'm going to actually call it down here. I have a nasty habit of saying, all right, let's do this, and then I run it, and I just never put the function in there, so nothing happens. So I'm going to put some stars in here just so we can see like a visual cue on the screen, because when we're working with threads, things might not go as we want. So entering and exiting, we're going to see the scope of this. And now I want to say Q shared pointer. All right, so we're creating the shared pointer. We now have this variable in this scope that has the class pointer in it as the data. So if we were to use QScopePointer, it would be deleted here when this goes out of scope. But we're using a shared pointer, so we can use this whenever we want. Whew. All right, now for the tough bit. and I want the QThreadPool global instance, and I want the max thread count. And from here, I'm going to say I++. So really all we're doing is saying from 0 to the maximum thread count, let's do some stuff. And we're going to say myRunnable. Screwed that all up, myRunnable. There we go. Again, people are going, wait a minute, we have a dangling pointer there. Well, what we're going to do is we're going to say runnable set auto delete, and we're going to make sure that's true just because I am very untrusting of platforms. I love Qt to death, but don't get me wrong, I love it to death, but I don't trust it. So I'm going to set that to true. I'm going to say runnable, and we're going to go ahead and set the pointer. And this is going to be our, you guessed it, Q shared pointer, my class. So what have we really done there? Well, we've taken this from one scope to the other, and we've passed that data back and forth. Very cool how that works. And then we're going to say QThreadPool. And we're going to grab the global instance again, and we're going to just start our runnable. Bang. So what's going to happen when we fire this bad boy off is it's going to start here, go to test, go up here, you're going to see entering, it's going to create some threads. Each thread is going to, when we go into our class here, actually let's go into the runnable first. It's going to go in here and then it's going to say, hey, I want to take this current thread and sleep for a certain amount of time. And that's why I put these stars here, because you'll see that this will go out of scope and those threads are still living in the background. Whew. All right, so anyways, and then it's going to say pointer, add count, and then it's going to go in here. And add count's just going to increment it. And because we're working with threads, I wanted to use a QMutex locker. Not making any solid guarantees that I've done that correctly, because really what we're focused on here is, you guessed it, the shared pointers. All right, let's save and run, see what happens here. And it's just going to go and go and go, and then destroyed. All right, so if we go up here, you can see entering, exiting, and then did a bunch of stuff and then destroyed. Bang. So the final count was 80, and it's incremented it, hopefully correctly. But what you can see here is that this thing just works, and it works the way you'd expect it to. So not super hard, and we don't have to really screw around with memory management. And before I close this, let's just assume I screwed something up in this code somewhere, somehow. When this application's destroyed, it's going to go through and try to, because we have this in here as a Q shared pointer, it's going to try and wipe out that memory for us. Pretty cool. Okay, so far we've talked about Qt-centric technologies, but it doesn't mean you have to use Qt. There are smart pointers baked right into the C++ standard library, and this is just what we're going to demonstrate here. So if you're already familiar, feel free to skip this video. Specifically, we're going to cover unique pointer and shared pointer. So I've already got a test class out here, and very simple. It's got a constructor, deconstructor, and a test, and it really doesn't do anything special. It's not curing cancer, just constructed, destroyed, and then some sort of value. And we can actually just fix that a little bit here. All right, so let's dive on in here. And first thing we're going to do is get our includes. And we're going to including Qdebug, IOStream, memory, and my class, this guy up here, and using the namespace std. From here, we're going to create some functions. I love functions. So void test IQUE, we're going to test unique, and then we're going to test shared. And let's just dive into our unique function here. And I'm going to say QInfo and I'm going to say I want the unique pointer And as I'm typing, you may be wondering, wait a minute, if this stuff is already baked into the standard library, why does Qt even bother to do it? Well, you have to remember that some of the things that Qt didn't even exist in the standard library when Qt made them. Qt made them because there was really nothing out there. That's actually why Qt was created right from the beginning, because there really was not a solid cross-platform GUI system, for lack of a better term. All right, so from here we're going to say P1 equals, and I just want to see what this looks like. So P1 get, and we can actually call the P1 test. Super simple, super easy to use. I mean, the standard lib. The real question now becomes, which one should you use? Well, that's a good question. So personally, if I'm working with Qt, I will stay with Qt-centric technologies, and I'll sprinkle in the standard library as needed. If I'm in the standard library, I will avoid Qt at all costs, simply because the standard lib typically doesn't know how to handle Qt stuff. All right, so what we're doing now is we're making a unique pointer, my class, called P2, and we're moving or taking ownership of this. Remember, this is a unique pointer, so only one. There can be only one object. So we have to take ownership of this bad boy. This is how you ensure you really don't have some sort of dangling pointer out there. And now that we've taken ownership, what we need to do is test these real quick. So I'm going to say P1, P2. This should be set to null. I should say null pointer because it's different than null. And then we're going to test P1. Pretty silly little test, but it really just, explains everything. I'm just going to say test the pointers. So we're going to say P1, and then let's test P2. That'll get super confusing if I don't change that. All right, so now we're going to just call this function here. Save and run, as long as I didn't screw up the typing. Voila. So we have the classes constructed, P1 equals this, and then from pointer 1, and then we've actually taken ownership on P2, and you see how P1 is now an Q object of 0, 0, meaning it's now a null pointer. There's simply nothing there. And then we have destroyed it. So that is the unique pointer. There can be only one. I always think of, what's that show with the sword? Highlander. There can be only one. Those of you who have never seen Highlander probably have no idea what I'm even talking about, but it's basically like he's this immortal guy with a sword, and he absorbs the souls of other people by chopping their heads off. So it's not a kid's show at all. Anyways, there'll be no head chopping here. So now we're going to test the shared pointer, and I'm going to just, before I forget, because I know I'll forget. Isn't that bad when you know you have a nasty habit, you just can't seem to break it? All right, so now we're going to say the shared pointer, my class, P1, and this is going to be a new my class. And then we're going to just grab this guy, and we're going to make P2. But we're going to say P2 now equals P1. That's right. So we're basically taking this variable and pointing it to the other pointer, or I should say both of these variables now point to the same instance out on the heap somewhere. Seems a little confusing, and it's kind of hard to wrap your head around. And then I'm going to just grab this, get rid of that because they both should point to something, right? And then I'm going to test those pointers. And we can also see how many references there are. So I'm going to say QInfo, and I'm going to say ref count. And then I'm going to say p1.useCount. And that should give us a count of how many other variables are pointing to that, how many references are out there. And in case you're wondering, yes, under the hood, that's exactly what's happening. It's reference counting. And once the reference count gets to 0, then the actual class is deleted off the heap. So, save run. See, I totally forgot to check if that was there. I'm glad I did that. So, testing shared, and then P1 and P2 both point to the same thing. And then we can use both of them independently. And we have 2 reference counts. And then once both of those are no longer referenced and the reference count is hit 0, bang, it's destroyed. Simple, easy to use, but you have to remember this probably didn't exist, or it didn't exist the way Qt wanted it to back when they created their smart pointer classes. And I fully expect that as time moves on, Qt's going to start deprecating those Q smart pointer classes and getting rid of them, and they will start favoring the standard library, would be my guess.